Hello, everyone, and welcome to today's Introduction to Machine Learning with Databricks webinar. My name is Singh, and I'm a US-based data and analytics consultant with Thorogood Associates. My contact details are on the screen should you want to reach out about any of the content that we discussed today. Also, just feel free to connect on LinkedIn, where we share additional content on Databricks, machine learning, and other analytics-related topics. So in terms of today's agenda, we're going to start by just introducing Thorogood and providing an overview of Databricks, just as some relevant context. We'll then discuss the basics of machine learning conceptually before delving into a hands-on Databricks demo, which is split into two different sections: data cleansing and transformation, and then also training and applying the machine learning model. We'll then share some information on MLflow, which allows you to industrialize machine learning solutions, therefore putting them into production. And then we'll conclude with next steps and some parting thoughts. So let's just start first with an introduction to Thorogood, and then after that, an overview of Databricks. Thorogood is a specialist data and analytics consultancy. We're independent, global, and customer-centric. Our consulting approach means that we seek to internalize the business objectives of any engagement, pair that with our data and analytics expertise, and then deliver quality outcomes for our clients. We have offices in the UK, US, Brazil, Singapore, and India. And then we offer a range of services, but the bulk of what we do is solution and development. So for example, using a tool like Databricks, but that also informs our ability to deliver strategies and roadmaps, trainings and empowerment initiatives, and also maintenance and support projects for our clients. Thorogood is independent in that we maintain close partnerships with many of the key vendors in our space. So a key partner for us since 2018 is Databricks. We enjoy close collaboration with Databricks across our offices in different regions. We were invited as one of 4 consulting launch partners for Databricks as they released their SQL analytics offering. We presented at their 2021 Data and AI Summit on the topic of machine learning and ML ops. And we're also continuously collaborating on joint marketing and customer initiatives. We also have established partnerships with many of the major cloud vendors, including Microsoft and AWS. We're a managed and a gold Microsoft partner in several relevant competencies. We deliver value in the data engineering, data science, and data visualization space for key enterprise customers, typically within data-rich industries like CPG, pharmaceuticals, banking, and insurance. Our key customers include Unilever, Johnson & Johnson, Liberty Mutual, Morgan Stanley, and many other blue chip enterprise organizations. Moving on, we can talk about Databricks. So Databricks, it comes from the creators of Apache Spark, which is an open source platform that's used for big data engineering and large analytics workloads. Databricks was founded as a private company to build upon the Spark Foundation and enhance it for enterprise organizational use. They created the Databricks service that they aptly refer to as a unified analytics platform, and now we'll talk a bit more about what that means. But first, the Databricks platform sits on major clouds, including Azure, AWS, and GCP. It gels nicely with other data platform offerings in those stacks, and it can also meet the needs of both data engineering and data science use cases. It's often a component of effective cloud data architectures. As it's a cloud platform, it's very effective at auto-scaling, so it's only going to use the compute power needed at that point in time. Its notebooks can also be authored in a variety of the most popular languages that are used by data scientists, engineers, and analysts. So that would be SQL, Scala, R, and Python. And today in our demo, we'll specifically be looking at Python. Some features of Spark that have been enhanced and are available on the Databricks platform are related to the data engineering side of things. It fits really well. Databricks fits really well with native Azure and AWS services of ADLS and S3. It also leverages the go-to data lake storage and Delta Lake, which is an open source offering created by Databricks, which just allows for a bit more structure and reliability for your data engineering in the cloud. And then on the data science side, it comes with a lot of libraries and packages pre-installed, which you can just kind of see on the screen: Keras, PyTorch, TensorFlow, XGBoost, scikit-learn, just some really popular libraries. And then there's also MLflow, which is created by Databricks, and it's released as open source, and it's an effective tool for machine learning model tracking. Now we can move on to discussing machine learning basics, and then after that we can go into our demo, which would be in Databricks. So the first thing to note about machine learning is that it's everywhere and its presence is only increasing. So some examples you may be familiar with are noted on your screen. Your email spam filter and your credit card's fraud detection service, they may use classification models to detect where an email or a transaction is likely to be unwanted or fraudulent based on relevant attributes. And Netflix or e-commerce websites, they may use cosine similarity models to recommend movies or products that may suit your taste based on the preferences of others with similar histories and tastes as you. So how does machine learning work? What are the key steps in the machine learning process? Well, you're going to start with some data. And as I walk through this hypothetical example, we'll have data on people that may or may not be professional athletes. So we'll have a data set containing information on a group of individuals, such as their height, weight, 100-meter sprint speed, their credit score, their eye color, their birth month, and of course, whether or not they are a professional athlete. These attributes, such as height, weight, and credit score, their features, and the label is whether or not that person is a football player. And where an output or label is numeric, like salary, it's a quantity, and we may well look to use a regression model to predict a quantity, which we'll get into more later. First thing we do is data cleansing, and then after cleansing the data, we split the data randomly into a training and a testing data set. We can select which features we want to use and how. So in this example, I don't think eye color or birth month will have as much bearing on whether or not someone is an athlete, but I definitely suspect height and 100-meter sprint speed would be correlated. So I would include those features in the data set, but remove things like eye color or birth month. We then select an algorithm for our model, and we'll explore how we decide on an appropriate algorithm to use in a moment. In this instance, I'm going to use a basic clustering algorithm that groups people based roughly on height and 100-meter speed into athlete and non-athlete clusters. We feed our model training data so that it can create these cluster groupings and establish the clusters of values that lean towards athlete or not. We then run our test data through this trained model in order to make predictions, and then this will allow us to understand how accurate our model is. We can see the result of the evaluation from our model alongside the actual values. So in this evaluation, we can look at how many athletes we correctly identified, how many non-athletes we correctly classified as athletes, and this will just allow us to refine the model going forward. We're able to iterate over time to refine our model by using different features or different algorithms as we deem appropriate. Ultimately, we can look to industrialize our model through the process of MLOps, whereby we automate the feeding of data into the model and the execution of the model. And we'll touch on this topic when we discuss the MLflow towards the end of the presentation. So I said we discuss it, but an obvious question, how do we decide which model to use for our machine learning problem? We can decide the model to use by using exploratory data analytics. So we look at facets of our data, including the distribution, feature interactions, missing values, variable type, and the need for accuracy. There are different ways to conduct exploratory data analytics. So for example, through data visualization and popular BI tools, or just data summaries, which is often available in analytics and ML tools like Databricks. Then we pick an algorithm, which in the world of supervised machine learning at a high level could be classification predictive modeling or regression predictive modeling. Classification, it uses groupings of attributes to categorize the data. And then regression, it defines a best fit line for the data so that the input values can return output values in line with the other data available. It's important to evaluate models to understand how they're performing, as was evidenced in the diagram previously. So to analyze a classification model, particularly a simple binary classification model with only two outputs, we can view the results in a 2x2 matrix that captures the true positives, which in our case are the correctly predicted spam emails, for example, the true negatives, which are the correctly predicted non-spam emails, the false negatives, or those spam emails that were classified as non-spam, And then lastly, false positives are those non-spam emails that were classified as spam. We can look at metrics such as accuracy, precision, and recall, and optimize based on the needs of our model. So for example, we may never want a spam email to make it through to people's inboxes, so recall would be more important than precision. Evaluating a regression model is a bit different. Effectively, on the left-hand side of the screen, you can see a basic linear regression model that is fit to some data. The vertical distance between data points and the regression line is called the residual. How we evaluate a regression model is essentially to calculate mean squared error and R-squared coefficient. These are different measures that describe how effectively our regression predicts values. Our model can also contain bias and underfit, where the model is poorly fitted to the data, or variance and overfit, where the regression is too specifically fit for the data. Now that we're done with the introduction to machine learning context, now we can move on to the demo, which is in Databricks. So we will switch over to Databricks now. Okay, so you can see that right now we're in a Databricks notebook. Notebook is just called data cleansing. In this notebook, we'll do just that. We'll cleanse the data and we'll perform some exploratory data analysis. For the data set that we'll be using, it's an Airbnb data set. So we'll get to this more in the next notebook, but what we'll look to do in this demo is predict the price for an Airbnb rental. So we'll have attributes of the rental, so things like the number of bedrooms, number of bathrooms, year it was built, whether or not it's a house or apartment, things like that. And we'll want to use those, to predict the price. So moving on, first thing we'll want to do is just read in the data. And you can see we do that here using PySpark. And this is the data frame that we read in. You can see it's just a table essentially. You can see there are many different attributes. So if I just scroll through, you can see all these different attributes. Some may be useful for prediction, some may be not. So if I scroll through to the right, you can just keep seeing there might be some that are useful. So for example, if we're here, like bedrooms, beds, bed type, room type, property type, these are all things that may be helpful to predict the price. So next thing we're going to want to do is, as you saw, there were many different columns that and just for simplicity's sake, we're not going to keep all the different columns that we just saw just because there were too many of them. So we're only going to keep a certain amount of columns from the data set, and these are the ones that we'll define as to keep. So we'll just select all these columns and we'll save them to a new data frame. And you can see it here. You can see that this is a much smaller data frame in terms of dimensionality, only having some relevant columns that we have. And we'll talk about feature selection more formally later. Now, the first transformation or the first cleansing activity that we'll make is converting data types. So if we take a look at this data frame, if we scroll all the way to the right and look at the price column, the price column, as you see here, it has a $sign. And because of that $sign, PySpark thinks that this is a string, when in reality, we're going to try to predict this using a regression model. So it should be a number. Machine learning models, they cannot interpret string values. And just to confirm that this is a string, if we expand this, it tells us a schema of everything. So we look here, price is a string. So we want price to be a double, which is a decimal. And that's just because you see like we have decimal values here. So that's the first thing that we'll do. We'll try to convert price from a string to a double. And that's what we'll do in this code cell. You can see we'll first remove the $sign, then just cast the column as a double. And if we look here, price is now double. And if we scroll all the way to the right, it should also have no $sign anymore. And you can see it's now a number. So it would be ready to use in a machine learning model. Next, we'll just do some data summarization, like just some things that we can see by doing this, some null values, extreme values, and the distribution of our data. So we can use the summary function on the data frame to do this. You can see we just see some basic summaries, so like mean, standard deviation, count, min, max, some percentiles. So we may get some information from here. More specifically, what we're going to look at is getting rid of extreme values. So if I just select the price column and do that summary again, you can see the summary for the price column. So you can look at the min and max. So look, if we look at the min, it looks like the min price is 0, max is 10,000. And min of zeros just seems kind of extreme. I mean, no one is renting out Airbnbs for free. So it will likely be an outlier. But ultimately, it's going to be the data scientist's job to decide what to do with extreme values. So maybe in some data sets, you might think that the 0 is appropriate to keep, so then you keep it. But in our case, we know that an Airbnb rental being a price 0 is likely just a mistake, so we should just remove it. So first, we'll just check to see how many prices are 0. You can see that it's just 1. So we'll just look to remove it. So we'll just specify that price needs to be greater than 0 in order to be included in the data set. So that's what we'll do here, and it'll remove that null value. And now, lastly, just handling null values. We don't want null values in our models just because they negatively impact it, because machine learning models, they don't know what to do with nulls. Machine learning models, they interpret numbers only. Models at the end of the day, they're just functions, so they need numbers. And that's why here we're going to look to handle these null values. And some different ways that you can do that. You can just drop any records that contain the null values. This should only be done if you have a lot of data, just because we all know the more data you have, the better a model performs. So if you don't have much data, dropping null values wouldn't make sense for you because you're just getting rid of more data. The next thing you can do is you can fill in the values. You can just try filling in the values of the column, or more formally, it's called imputation. So if a column is numeric, you can replace null values with the mean, median, or 0. If the column is categorical, you can replace them with the mode, and also just creating a special category column, which we'll do here anyways. Or you can use techniques like ALS, which are designed to impute missing values. It's important that when you do these things for imputation, creating an additional field that specifies whether a field was imputed would be a good idea. It just gives additional context to the model because you're indicating which fields have been imputed. So it might be able to learn things from that. If there's a specific reason why a column might have null values, a model may be able to pick up on that trend. So what we'll do now is we'll handle the null values. First thing that we need to do is PySpark, it has something called an imputer, which will basically just impute values for us. But the imputer requires numeric columns to be of type double. So what we're going to do here is just iterate through all the numeric columns that we want to impute, and then we'll just change the type to double. So you can see these are all the columns. So accommodates, bedrooms, beds, minimum nights, and so on. These are all the columns that we change to type double. And now we'll create the dummy variable that will indicate whether a value is imputed. So like I said, when you impute a value, it's a good idea to just indicate whether or not the value has been imputed, just in case that there's a trend that you're missing. So since these are all of the columns that we're going to impute values for, we'll just create a new column which would indicate. So if the column is null, the value is 1, otherwise it would be 0. So just taking an example of this, if we scroll to the right, you can see bedrooms NA. So bedrooms NA is 0, which means for this record, bedrooms is not null. So if we scroll, we'll see that for the first record, bedrooms is indeed not null. So it is behaving as expected. Next, just talking about transformers and estimators, since we'll be using them. A transformer, it accepts a data frame as an input, and it's going to return a new data frame with more columns appended to it. Transformers, they don't learn any parameters from your data. They just apply rules-based transformations or calculations to just prepare the data for model training or just generate predictions using a trained model. They have a dot transform method that actually performs the activities, or transformation in this case. The estimator is what learns or fits parameters from your data frame. The fit method is what allows this. So fit and train, they're pretty interchangeable here, as we'll see. So we'll import the imputer, PySpark.ml.features library. We'll give it a strategy, a median, essentially saying that we want to do median imputation. We'll give it our impute. We'll give the input columns in this case are our impute columns, the columns that we want to impute values for. Then the output columns, we'll just give them the same name. So it would just be the impute columns again. And now we have to fit the imputer to the data. And then after fitting it to the data, so essentially in this case, it's when we fit the imputer, it's basically just going to learn what the median is for each column. And now when we actually do the transform is when it will actually perform the imputation. So that's what we're doing in the next line. And after doing this, our data is all. So what we'll do is we'll just write our data frame to storage, and then we can move on to the next portion of the demo. So next would be training and applying the model. As I mentioned previously, we're gonna try to predict the rental price for an Airbnb unit. So we can begin by just importing the data that we just got done cleansing. And now this diagram pretty explains what we're going to do pretty well. We have our full data set, which is just that cleansed data set. We'll split it into a training set and a testing set. And our model will fit on the training set. So it will train on the training data, essentially meaning that it will learn the different patterns and trends that it needs to in order to make predictions. And after this model is trained, we're going to evaluate it on the test set. Essentially, we'll make predictions on the test set, and then we'll evaluate the accuracy of it to see how well the model did. And just to recap, the reason why we evaluate on the test set is just because the test set is unseen data. We didn't give it to our model for training. So because it's unseen data, it gives us a pretty good proxy as to what we'd see if we were in production, where in production, we'll always see unseen data. First thing we'll do is split the data into a training set and test set. So our training data frame will be 80% of the data, and you can see that we're using the random split function to do this. And then the testing data will be 20% of the data. So now that we've split the data into training and test sets, we're now going to establish a baseline model. So a baseline model, what it really is, it's really in the name. It just gives us a baseline of performance. And the reason you want to establish a baseline is just so you know, just so you have a benchmark for your model. The idea of a baseline model is that it's supposed to be a simple model. So the idea would be that any machine learning model that you train, it should perform better than the baseline, because the baseline is a simple model that was essentially easy to come up with. Machine learning is complex. So if your machine learning model cannot do better than a baseline, then it means you should just go with your baseline. Since your baseline is already there, it performs better than your machine learning model. It will be easier to put into production. So it means you can just go with that model. So the goal with a machine learning model would just be to perform better than your baseline. So in our case, our baseline model, we will just use the average price. So we'll just take the average of the price column and predict that for each record. So if you look here, average prediction, it's just the average of this price column. So you can see we predict 215.27, so $215.27. We just predict that for each record, and that's going to be our baseline model. And as I mentioned, this is just a really simple one, and that's the goal with the baseline. What we can do now is evaluate this baseline model using the root mean squared error, which is a pretty common way to evaluate regression models. You can see a root mean squared error of 178.9. Now, the goal, as we move on with this, we'll train a machine learning model. We need to beat this baseline, as in, well, we need to perform better than it, which means a lower root mean squared error value. So today, the model that we're going to use a very simple linear regression model. We're going to try predicting price using just the bedrooms column. And it's always a nice idea to start off simple with machine learning and just iterate as you go, just so you don't need to have a more complex model than you need. So first thing, let's just look at the price in bedrooms. We just have them here. These are the two columns that we'll use in our model. Next, we just take a look at another summary of it. Looks like looks like the minimum value for bedrooms is 0. Max is 14. And like I mentioned previously about outliers, if this seems abnormal to you as a data scientist, you would remove it. In this case, we will just keep it. And now moving on, let's just try to fit our linear regression and see what happens. So we'll import our linear regression, and then we'll specify the features column, which is the bedrooms. And like I said, we'll just have a single feature in this model. The label column, which is a price, so what we're trying to predict. And then we'll call the .fit method, which we use to train our model. And you can see we get this error here. Essentially, it's saying column bedroom must be of type vector, but it was actually of type double. So what's going on here is PySpark wants the features column to be of type vector. So if we scroll up here, bedrooms is just a normal column. It just has values in it. PySpark wants each of these records to be a vector. So the fix for this is pretty easy. We can just transform the bedrooms column into a vector. So to do this, we would import something called the vector assembler, which just does that. It transforms columns to vectors. We give it our input column, which is bedrooms. Output column, we'll just call it features. So we will then transform the data. And if we display the data, you can see all the way to the right, the features column, which is just the bedrooms column in vector form. So you can see here 1, 1. These are just the values for bedrooms, but now put into a vector, you can see 2 and 0 as well. But now that we've done that, we can now train the model. So we'll specify the features column, label column as price. We'll fit the model, and then it looks like the Spark job did complete, so no errors there. And now we can just print out the formula. This is a linear regression model, so it might be helpful to take a look at the formula. Y equals under 23.54x plus 50.09. Lastly, what we need to do is we need to make predictions test set because we need to evaluate this model. So what we'll do here is first we'll transform our test set using the vector assembler just so the bedrooms column becomes a vector. Then we'll use the transform method of the linear regression model to actually make the predictions. And you can see the prediction column here. So these are so you can see the actual price and then the predictions here. So now on to evaluation of this model. We'll use root mean squared error again, just to keep things consistent with the baseline. And you can see the root mean squared error is 149.55, which seems like a significant performance. It seems like a significant performance increase from the baseline. So we did beat our baseline model. So this would just indicate to us that machine learning likely would be a good endeavor for this project, just because we use a simple model. We were already able to beat our baseline. So now next steps would just be iterating upon this model, which would mean adding more features or trying different models that might be more complex. So now that we've talked about this, I just want to head back to the demo and talk about productionization of machine learning models. So let's just go back to the presentation now. So after evaluating the model, we move on to putting the model into production. This is where we see some challenges come up. So first, keeping track of experiments and model development. Data scientists are often going to run hundreds, if not thousands, of different experiments. So it's important to keep track of them if you ever want to run a particular experiment again. Next is reproducibility. You want to be able to reproduce an ML experiment because it allows you to get the same results consistently across different environments. So for example, going from a development environment to a production environment, you want to ensure that your model is reproducible so that it is able to integrate seamlessly into the production environment. Then we have comparing models. So when you run a large number of experiments, your ultimate goal is going to be to find the model configuration that gives you the best results. So you need an easy way to compare different models. And then lastly, the standardization of packaging and deploying models. We want our users to be able to use our model in order to make predictions that provide value. And that's why we need a way to deploy our model to end users in a standardized way, just so that we won't run into any issues when deploying the machine learning models that are created using different technologies or libraries. One solution for these problems that I just listed is MLflow. MLflow is an open source platform for managing the machine learning lifecycle. It's developed by Databricks and comes pre-installed on Databricks machine learning runtimes. The 4 key components of MLflow are tracking, projects, models, and the model registry. First, talk about tracking, which saves the code, configuration, results, and artifacts of an experiment. And by artifact, I just mean files like the model itself or any graphs that you may have created. Then there are projects, which is just a format for packaging data science code so that it's reproducible and reusable. And next, there is MLflow models for providing a standardized format for deploying machine learning models, regardless of the library used to develop the model. And then lastly, there's the MLflow model registry, which is a service for centralized model management, review, and sharing. This includes aspects like model lineage, which is just the experiment and run that produces the model versioning, and deployment endpoints. So we'll quickly take a look at MLflow. So back to the demo. We're still in that same notebook training and applying the model, but now the MLflow portion of it. So in this cell is where we actually use MLflow. To use MLflow, since MLflow is integrated in Databricks, it's quite easy to just get it up and running here. So I will show that here. You can see the way we start MLflow is with the statement MLflow.startRun. We give our run a name, LR single feature. So just something descriptive. So LR linear regression. So linear regression single feature, which pretty much captures what we're trying to do. And essentially what we're doing now is within this MLflow run, we do the same steps that we did above, but now we're doing them within this MLflow run. So MLflow will know to log all this or save this run to MLflow. And I'll show you exactly what that means in a second. But yeah, you can see it's all the same things as before. New things that we do is that we log different parameters. So you can see we log a parameter called label, which the value we give it is price bedrooms. We log the model itself. So this just saves our model so that if we do want to make predictions with it, we can just import the model. It's already been trained, so we won't need to retrain it. And then lastly, we'll log a metric, which in this case is root mean squared error. And then also, if we want to log an artifact, we created this graph, we can log it as well. And I'll just show you what this means. So if we go to this experiment and just go to this link, you can see all of our different experiments here. We'll talk about these experiments later, but we'll just look at the linear regression single feature just so you can see everything that we've logged. You can see the parameters, label, price bedrooms that we talked about, the metrics, root mean squared error, which we also logged, and now the artifacts. You can see that the graph that we logged is here. And then in addition, we logged the model as well, and that's what this model folder is. If we go here, MLflow gives us instructions on how we can import this model to make predictions. So, and that was a product of us logging the model. So you can see here that by using MLflow, we've essentially just saved our model run. Everything is here so we can look at the different metrics to evaluate the model. We can, since our model is saved, we can then import it. So it just gives us a good way to keep track of our experiments. And just to illustrate the point further, in machine learning, you rarely just run one experiment. So in this case, LR single feature is just one model. We're going to run many different models with many different parameters and maybe even different data sets as well. So I'm just going to show that by doing some more MLflow experiments. You can see we use MLflow.startRun, and we'll just change the model. So we use a decision tree, and you can see we changed the run name as well to DT single feature. We'll do the same. We'll do another one. We use a gradient boosting tree, and then lastly, we'll use a random forest. So now these are 3 more experiments, and that's what you see here in the MLflow dashboard. If we head back to it, you can see these are all the different models that we've logged. And you can all see their root mean squared error. So I just sorted from least to greatest. You can see that the linear regression did perform the best. So you can imagine in an actual scenario when you're working on an actual machine learning projects, you probably wouldn't just have 4. You'd have hundreds, if not thousands, of different models that you try out. You would conveniently have them all in this one location where you can then just look at which model has the best root mean squared error. You can click into them, and then you can also import the models to make predictions. Now that that's done, we'll just head back to the presentation to wrap things up. So now that we're at the end of today's session, I hope you found it useful. We have some offerings at Thorogood that may be of interest to you to continue your Databricks learning. Whether you're just getting started with your Databricks journey, we have a Databricks workshop or a proof of concept solution to enhance your data and insights with Databricks. And if you have any other questions or are interested to learn more, please don't hesitate to reach out. Thank you for joining. This will conclude the webcast.